right, class. Um, Good afternoon, and I hope you're all doing well. Um, let's see. I had a pretty good weekend. Most of my items for my forge are arriving or have arrived. I got my tongs this weekend. I got uh, my sledgehammer, my 3-pound sledgehammer. I got my whetstone so I can sharpen. So I should be attempting to forge my first knife this weekend, I hope. Hey Jackson, hey Charlie, hey Akshay. Thanks for watching. Um, Next week, I'm going to assign some kind of a final exam. Just since we've been doing all this review, and I think I'm going to give you 3 days to work on that. So we'll take 3 days off next week, and then I'm also going to be doing a poll, submitting a straw poll for you guys to fill out with asking you guys what you want to learn next, because we're done with content, and so we can kind of learn something else. So I'll give you guys some options for special topics. Hey Spicy Pepper, hey Sam, hey Sofa. All right, so this is a paper 3. This is the May 2019 Time Zone 1 paper 3. And paper 3 is a little bit different from paper 2, okay? So I want to go over what it says. So there are 2 sections. There's section A, and then there's section B. Now, section A, see how it says answer all questions. So what that means is, so you'll get 2 or 3 questions that are on data analysis, okay? So the section A questions are on data analysis, and everyone has to learn data analysis. Section B, you don't have to do all the questions. So you'll actually find that paper 3 is the thickest paper when and if you actually take the exam. I know some of you who are doing SL will never take the exam, but and so there are a couple of different options. There's relativity, engineering physics, imaging, and astrophysics. I taught you guys the engineering physics option, okay? So that's questions 6 and 7. All right, so engineering physics has it has rotational dynamics, and it has PV diagrams, essentially. So that's what I taught you guys. I would love to teach you about these other items, but they're kind of outside. They take us too far away from the main thrust of the class, so I don't know, it's just easier to fit engineering physics in. All right, so let's get down to it. Today, I'm going to be doing questions 1 and 6. So notice how, now by the way, when and if you actually take the exam next year, you could do the option A if you wanted to. There's nothing to stop you from doing option A, but I would strongly advise against it because I didn't teach you anything about relativity, okay? So basically it's it's like you're destroying your exam grade if you don't do the option that I taught you. So that would be engineering physics. You guys will be doing questions 2 and 7, okay? So I'm going to start off with question 1. It says, in an experiment to measure the acceleration of free fall, a student ties two different blocks of masses m1 and m2 to the ends of a string that passes over a frictionless pulley. Student calculates the acceleration of the blocks by measuring the time taken by the heavier mass to fall through that distance. Their theory predicts that A equals bleh, which can be arranged. This can be arranged to give bleh, so they get the acceleration. In a particular experiment, the student calculates that A equals blah, M1 equals blah, and M2 equals blah. Okay? Calculate the percent error in the measured value of G. So, like I said, part A of the paper 3 is going to be about data analysis. So this question is about propagation of error. Okay? So if I look at M1 plus M2, remember, when things are added or subtracted, their absolute uncertainties add. Okay? So what is our, if I quote a value for M1 plus M2, I want to add this number and this number to get 0.245. Then the uncertainty would be this uncertainty added to that uncertainty. So I get plus or minus 0.002. All right? And because I'm going to need it later, let's just calculate the percent uncertainty. So the percent uncertainty is 0.8%. Okay? Now, if I look at M1 minus M2, I'm going to take those two numbers and I'm going to subtract them. So I'll get 0.005 when I subtract them. But even though I've subtracted them, you still add the absolute uncertainties. So we get plus or minus 0.002 again. All right? That is a percent uncertainty of 40%. Okay? Quite a large uncertainty. Then we look at G. The acceleration. The acceleration's value is 0.204 plus or minus 0.002. That is a percent uncertainty of, let's see, 2 divided by 204 times 100. That's a percent uncertainty of about 1%. Okay? So if I look at my actual formula for G, it's three things. It's A times M1 plus M2 divided by M1 minus M2. So these are three things multiplied and divided by each other. So when things are multiplied or divided, we learn that the percent uncertainties add together. So the percent uncertainty in gravity is going to be the percent uncertainty in acceleration, which is 1%, plus the percent uncertainty in M1 plus M2, which is 0.8%, plus the uncertainty in M1 minus M2, which is 40%. Okay? What do you want to bet that the next question is asking us, like, why is this a horrible way of measuring gravity? I think that's going to be the next question. So that's roughly 42%. is the percent uncertainty. Okay. Oh, maybe that's going to be the third part. Ah, there it is. Oh, my computer's freezing. There it is. Okay. So deduce the value of G and its absolute uncertainty for this experiment. So what you want to do, if you want to calculate the value of G, is you use your best guesses for all of these quantities. So my best guess for the acceleration is 0.204. My best guess for M1 plus M2 is 0.245. And my best guess for M1 minus M2 is 0.005. So working that out, I get 9.996 meters per second squared. Now, the uncertainty is 42% of that. So 42% of 9.996 is equal to 4.19. Now remember, we round absolute uncertainties to one significant digit, so I'm going to round that to 4. And then I round this to the same place value, so I'm going to round that to 10. So our quoted value for G is going to be 10 plus or minus 4 meters per second squared. All right. So part B. Part B says there is an advantage and a disadvantage to using two masses that are almost equal. State and explain the advantage with reference to the magnitude of the acceleration that is obtained. Okay, so if M1 is approximately equal to M2, then when we look at this system, it's almost balanced. And if the system is almost balanced, then that means that the acceleration is going to be very low. So, they're almost in balance, so the scale is going to tip very slowly. So the measured acceleration will be small. Okay? So the measured acceleration of one of the masses falling is going to be small, which is easier to measure. Right? Wouldn't you agree that it's easier to measure something that's falling slowly than to measure something that's falling rapidly changing speed? Okay? The second part says, what is the disadvantage? Well, the disadvantage is if M1 is approximately equal to M2, then the percent uncertainty in M1 minus M2 is huge. See how when we subtracted these two, we got 0.005 plus or minus 0.002, which is a 40% uncertainty. Okay, that's a pretty huge uncertainty. And then when we propagate that error, because remember, the uncertainty in M1 minus M2 impacts the uncertainty in gravity. So I would say this uncertainty propagates into the uncertainty in gravity, giving it a large, I would just say making it very uncertain. Okay? So that's what I would say. So I think that concludes question 1. So you can definitely 100% expect to be questioned on propagation of error. Okay? All right, then the other question I was going to do was question 6. Okay, so scrolling down to question 6. All right. Oh, so this is almost the same thing. A solid cylinder of mass m and radius r is free to rotate about a fixed horizontal axle. A rope is tied around the cylinder, and a block of mass m/4 is attached to the end of the rope. The system is initially at rest, and the block is released. The moment of inertia of the cylinder about the axle is 1/2 mr squared. Okay. So first of all, we want to calculate the angular acceleration of the cylinder. So if we look at this, let's focus on this picture. Ooh, I think the mail just came. I'm going to check the mail. It's like the most exciting part of my day is checking the mail. Oh boy, I got a book. Let's see what it is. Sweet! Principles of Modern Chemistry. You guys ever shop on abebooks.com? abebooks.com, you can get used textbooks. So I bought this textbook for $6. And do you know how much this textbook costs if you buy it off Amazon new? It costs over $100. So $6, free shipping. Why did I buy this book? Because I took AP Chem in high school, and because I took AP Chem in high school, I didn't have to take it in college because I got a good enough grade on the AP exam, and I subsequently forgot all my chemistry. So I'm going to relearn chemistry. So yeah, I feel like that's a hole in my understanding. I have a very good understanding of physics, but the chemistry part I'm sort of lacking. So, all right, let's get back to this question. Better put my knife away. By the way, because I got my whetstone, I can actually sharpen this knife. It is a steal, I agree. Oh, and by the way, this textbook is written by David Oxtoby, which is, I believe, a professor at one of the Claremont colleges. Let me look it up. David Oxtoby is the president of Pomona College. Does anyone know an Oxtoby? Does anyone know an Oxtoby? So maybe I should have just emailed the guy directly and said, Yo, Dr. Oxtoby, I'm a teacher in your town. will you send me your textbook for free? I bet I could have done that. All right. So what we have here is we have this mass is translating. This mass is translating. And so because this mass is translating, I'm going to use Newton's first law for it. It's T minus mg, but the mass is m over 4, equals m over 4 times its acceleration. Okay? So that's net force equals ma for this mass. Okay? Then this mass is rotating. So I'm going to use torque, net torque equals I alpha. Okay? So what is the net torque? The net torque is due to the tension in the rope. Okay? Now you might recall that the formula for torque is force times R. So we have tension times R is the net torque, and that equals I, which is 1/2 mr squared, times alpha. Okay, now I can simplify that to tension equals 1/2 mr alpha. Okay, so that's the amount of tension. Then what I'm going to do is I'm going to plug that in for the tension. So I have 1/2 mr alpha minus m over 4 g equals m over 4a. So now you'll notice that all the m's cancel out. And then you might recall that when something is spinning, you have v equals omega r, which also means that a equals alpha r. Okay? One thing we have to be a little bit careful about for this problem is that if the mass, there needs to be a minus sign in here, because if the mass accelerates downward, that means that the angular acceleration is positive. So I'm going to notice that this right here is negative a. So I have minus 1/2 a minus 1/4 g equals 1/4 a. All right. So then I get, what we get is minus 1/2 minus 1/4 times a equals 1/4 g. 8. What did I just do? Oh, this should be 2 and 8. Yes. So I have let's see. I've made a mistake somewhere. I'm just going to multiply both sides by 4 here. So I get 2, I get 1, I get 1. So that means that the acceleration is 1/3 g. Okay. Then alpha equals a over r, so I just get g over 3r. So that's a little bit tricky. It involves a system of equations. Oh, hey, Christian, thanks for showing up. All right, part 2, show that the tension in the string is mg over 6. So what I can do in that case is just take one of my equations. So, for example, t minus mg over 4 equals m over 4a. And then I can use my expression for the acceleration that I calculated. So I get t minus mg over 4 equals minus m over 4 times g over 3. So I get t minus mg over 4 equals minus mg over 12. So I get t equals 1/4 minus 1/12 mg, which is so 3 and this one. So I get mg over 6. All right. Part B says the block falls a distance of 0.5 meters after its release before hitting the ground. Show that the block hits the ground 0.55 seconds after release. So this is just a kinematics problem. We're going to use delta x equals 1/2 at squared. So the delta x is 0.5. And we know that the acceleration is 1/3 g from this part right here. So we have 10 over 3. That's 3.3 t squared. And then I solve for t. And I get 0.55 seconds. So I did that part. So that was just a basic kinematics equation. All right, let's go to part C. The following data are available for the cylinder at the instant just before the block hits the ground. Calculate the angular momentum and the cylinder and the kinetic energy. All right. So we have the formula for angular momentum is I omega. We learned that. So we got to figure out what is the omega. Well, let's go ahead and go back to this one and figure out what is V final. So V final equals V initial plus AT. And I know that V initial is 0. I know the acceleration is 3.3. And I know the time it takes is 0.55. So that means that V final is 3.3 times 0.55, 1.8 meters per second. Okay? Then I know V equals omega R up here. So I have 1.8 equals omega times 0.2. So that means that omega final is 9.1 radians per second. Okay? So the angular momentum is going to be 1/2 mr squared. So 1/2 times 12 times 0.2 squared times omega, which is 9.1. So that's 216 kilogram meters squared per second is the angular momentum. It's a little bit tricky. And then the kinetic energy. The formula for kinetic energy is 1/2 I omega squared. So we have 1/2 times 1/2. The inertia is 1/2 times 12 times 0.2 squared. And then omega final is 9.1. And we get 9.9 joules. Okay? So I think that's a little bit tricky, but one of the things I want to point out is that you're going to get points. Like in all of these problems, if you take a stab at it and just use this equation, L equals I omega, you're going to get a point for this one, okay? If you use 1/2 I omega squared for the second part, you're going to get a point. If you use a kinematics equation here, you're going to get a point. If right here, if you throw, if you take this problem and you throw Newton's second law at it for rotations and Newton's second law for linear motion, you're going to get a point. So basically, you can get over half the points or half the points just by knowing which equations to use. And when passing the IB exam is, passing the IB exam could mean getting 30% of the points. It's like you're already going to pass the exam if you just know which equations to use, even if you don't know all the details of this, okay? Which are pretty tricky. All right, that's my lesson for today, and I hope you guys have a great afternoon, and I'll be posting a straw poll for our after final exam topics this afternoon, so I'll send out another reminder for that. Have a good afternoon, everybody.